This morning we've got the last full-on session of DNA talks, and this first session of the morning is dedicated to the Y chromosome, which is interesting in many crime cases. So we have Mikkel Andersen first, and there's and Kurt Kaliber will be next, also speaking on a Y chromosome topic. So thanks very much, Mikkel.
Thanks, David. Thanks. Just see if this is on. So, is it on? Can you hear me? Good. So first of all, thanks for coming, everybody. That's nice, and thanks for the organizers and the Newton Institute to be able to do this stuff. That's amazing. So as David mentioned, today I'm talking about the Y chromosome and how to assess the evidential value of the Y chromosome. And this is joint work together with two colleagues, Paul Svante and Niels Morling. But I've discussed together with many of you guys as well, Mikkel Kaliber, Richard Gill, Julia Serrata, Bruce Williams, and others. So it is really joint work together with many people. This works. Okay, it does. Good. So the talk has two major parts and a minor one. So I'll start out by quickly do a recap of the discrete Laplace model for you who doesn't know it. Then I'll do two larger parts of the talk. So I'll talk about how to compare likelihood ratio estimators, and I'll talk a bit about the population substructure as well. Okay. So just as Teresa talked about yesterday, really the motivation of the discrete Laplace model was to make a statistical model of the haplotypes. So put on a probability mass function on all haplotypes, basically. So the idea of that was to be able to do a lot of different stuff, but not have a new tool for each task. So if I have a statistical model or have a probability mass function for the haplotypes, I can do likelihood ratios, I could do match probabilities with population substructure corrections, I can do mixture deconvolutions and other stuff. So in that way, sort of, that would be nice to have a model. So the idea behind the model is that we know the loci are not independent on the Y chromosome. So the idea is to condition on something to obtain, now I write independence. So we obtain conditional independence. So that's the idea. Okay, so here are a lot of formulas. The first one up here, that's just the discrete Laplace distribution. So that's a known distribution. What we did in our 2013 paper, we showed that it's actually an exponential family. Okay, so that's a nice property to be able to make inference in a clever way. The discrete Laplace model is just a finite mixture model, just as Martin talked about yesterday. And the part that sort of makes it stand out is that if you condition on a central haplotype, then the distances between the central haplotype to another haplotype, these distances are assumed to be independent.
So how are you measuring these haplotypes?
Okay, so I didn't.
Numbers,
yeah, we're only looking qualitative.
Tell me about your data.
It's alleles, just allele numbers. So number of repeats. So we only have qualitative information.
So looking at what
I'll give you an example in.
You need to see the biology.
So here is the biology. So that's a distribution. So it's allele numbers. So we have a locus, DYS 392, and then we have some different repeat length. So that's the only part we're looking at. So we don't look at peak heights or anything, we look at normal STR alleles. Does that answer it? Is that okay?
These are all on the Y chromosome.
Yeah, all on the Y chromosome. Okay. So that's the data we have. These are integers, so we have support on all the integers. So we are on the lattice, and we have a mass function on all these. Okay, another.
And R is the number. The subscript R is the number of
loci.
Loci, yes.
Yeah. So another.
And C are some sort of sub.
Yeah, it's the number of components in the mixture, some kind of subpopulations or number of clusters or. Yeah. And another part of the model, which is also important, is that we do not estimate. So sorry, this distribution up here has two parameters. It has a dispersion parameter P and a location parameter mu. Okay, so that's of course important. So this mu corresponds to a central haplotype here. So we measure the distance between these two. And P is the dispersion parameter. but we do not estimate a single p for each locus in each subpopulation. We estimate some parameter for each of the components or each of the subpopulations, and one for each of the loci, and then we do some stuff here, and that's in order to sort of reduce the number of parameters in the model. And that's easy because we have an exponential family up here. So the estimation in this model, we use an EM algorithm just like Martin told about yesterday, and we have some certain an EM algorithm, and because we have an exponential family, we do a GLM fit within each iteration.
Am I right in thinking that you're allowing negative repeat numbers?
Yeah.
Say a bit more about that.
Not for now, no. so you, yeah. So that is a point. So we say that we want probability on all integers. If you didn't sort of assume that, you hope that the tails are really small, but if you didn't assume that, you need to put in some boundaries of sorts, and that's difficult as well. So that, I mean, that's what we did. So, and it doesn't seem to be, I mean, it seems to be okay. It has some advantages that you actually can deal with alleles that you haven't observed, and that can be important in mixed deconvolution, for example.
So why is that so difficult? You can just truncate the distribution at zero or something? Is that computationally difficult? Or?
Sorry, that?
Why is it so difficult to truncate this distribution at zero?
I guess the estimation becomes quite difficult, would be my impression. Sorry?
Normalization comes.
Yeah, exactly. Yeah. So you don't have an exponential family any longer, and that quite heavily relies on that fact for the estimation to be efficient.
Sorry, it would be an exponential family. If you show it's just multiplying it by a different measure, which and it doesn't stop it being an exponential family. Yeah, no,
Could be.
Yes, yeah.
Okay.
It will be an expression. It should be. Yes, it is.
Okay. Good. Well, try to look into that. Might be a good idea.
No.
Okay, I think I'll try to move on sort of in for the time. So I'll skip the first example and no, yeah. So the biology we have. This is an allele distribution for a particular locus from 700 German people, and we try to fit this model. We pick one component, two components, three components, and we compare. So the gray one, the bold one, is the observed one, and the blue one is what the model predicts. Okay. We have observed a bimodal distribution. Picking one cluster is not good. Two clusters seem to fit okay. The central haplotypes here is 11. Over here we have 11 and 13. So I'll just go through that quickly. Moving to two loci, we can see that the 11 allele before is actually spread out, so to speak, on three different alleles on that locus, whereas the 13 one is centered at a particular allele for that one. And we can also try to estimate that distribution. And we do that by, seems the best model fit would be 9 components, and these are the central haplotypes for these 9 components, and the a priori probability of originating for each of these. And we can compare the predicted and observed as well. And then I just want to briefly talk about the number of parameters in the model. So if we have this 2 by 2 this table of 2 loci, and we wanted to have a probability for each of these alleles, we would need 56 parameters. In this discrete Laplace model, we only need 36 parameters. So that way, by imposing this certain structure and distribution, we sort of save some parameters. So sorry about that being a bit quick, but I have to move on. So now I want to talk about estimating or comparing estimators of the likelihood ratio. So we are in the case where we have a single source stain, and we assume that there are no typing errors, and we have no peak heights. So we have just a single profile with the alleles, and we want to try to evaluate the evidential value of this match if the suspect matches the stain. Okay. There are different estimators, and I'll get to them in a second. But what's difficult about comparing these estimators is that they actually estimate different values or different population quantities, because some use data reduction. Some only look at haplotypes as a name or a color. So the quantity they are estimating is something different than the population frequency. So that's an important part. So again, we have a case. We have a profile from the donor to the crime scene stain. We have a suspect, and we have a reference database. So what we've done in this study is try to look at it as a decision problem. So is the suspect the donor? That's sort of the problem we're trying to decide on. And we want to use the likelihood ratios to decide on that. And normally, if you knew the population frequency, in this simple case, you would use that. And again, for this kind of decision scores, the higher likelihood ratio, the more evidence that the suspect is the donor we have. And of course, if you do data reduction, you can sort of just say, in this kind of case where we have a crime case, you can say that if we do not have a match, we report a likelihood ratio of 0, and if we have a match, we report 1 of 1. But that's not really informative. So we want somehow to be able to distinguish between being conservative and informative. So
Sorry, who's reporting a likelihood of what? Ratio 1?
no, so that would be a very an uninformative way to do it. But that would like do it. You would be conservative by doing it.
Sure,
Yeah, but that's not an informative
Are
estimator.
people actually doing that?
No.
I'm glad to hear that.
So we have a population. So the idea is to be able to simulate cases where the defense is correct and cases where the prosecutor is correct. And to do that, we have a population. We took the European population from the PERPS dataset, having 12,200 profiles. We then simulate 1,000 cases under the prosecutor's hypothesis. We do that by sampling a reference database and simulating the suspects, which is the same as the donor's haplotype. Okay, and we also simulate 500,000 cases under the defense, so where these two are different. So we simulate a reference database, we simulate a suspect, we simulate a donor. Often it's the case that these two do not match, which corresponds to like a ratio of 0. I'll get back to that in a second. Okay, it turns out that we have 1,000 prosecutor cases where we do have a match. Of these 500,000 cases where the defense is correct, 9,000 of these is a match and a lot is not a match. So to talk about the different estimators we have been looking at. Normally you could consider the haplotypes as being names, and it's often the case that we have a rare haplotype. So a rare haplotype is one where it's not a part of the reference database. So one simple way to do the stuff is what is called the binomial estimator. So you add the haplotype to the reference database, and your match probability is 1 divided by n, meaning that the likelihood ratio is n. But several studies have shown that that's actually a too low likelihood ratio. It's not that good. So different approaches has been made to try to improve this. And there are two. It's the Kappa method by Charles Brenner and the generalized good by Julius Serrata. And you can look at them as the binomial likelihood ratio inflated by some constant for both of these. There are different arguments for the two methods, but what they do is inflate the likelihood ratio, and they look at haplotypes as names or as colors. And then there is the discrete Laplace method, where we use the genetic information. So these are quite different. It would also be interesting to talk about the coalescent method that Amke is going to talk about next, but that's computationally quite still difficult to do, so we skip that one, but it would be interesting if it's going to be faster. And then Julia is working on a Chinese restaurant process that would also be nice to include, and we're working on trying to do that. Okay, so as I mentioned, I restricted to rare haplotypes, so haplotypes of the suspect that is not a part of the reference database you have. So that's the difficult ones. So we're down to 460 cases where the prosecutor is correct, and of the defense, 800 have a match, and 200-some thousand do not have a match. So the first thing to do you could do is to look at the distribution of the likelihood ratios of these estimators. The most right one here is the population likelihood ratio. So that's if you use the population frequency of the haplotypes. Had you known it, you don't know it, but because we have a simulation study, we do know it. And you see that we have a separation here. So in generally, the likelihood ratio where the prosecutor is correct seems to be higher than if the defense is correct. And that's the same case you have for the discrete Laplace model over here. And then there's something called disclap less, and that's if I restrict it to 3 loci instead of the 5. So that's just another way of doing data reduction, basically. And then we have the Kappa method by Brenner and the generalized good here. And you so you see how these distributions are. Okay, so the next slide is probably the prettiest rock curve that you have ever seen. So what this shows is that if you use these estimators on the decision problem as to say whether the suspect is the donor or not. You get something like this, and all of these other estimators is below the black one. And that's due to the fact that in a majority of the cases, we do not have a match, so we report a like ratio of 0, and that's good. So we have to zoom in, so let's zoom in on this false positive rate here. And then we get something that we can look at. So as you see, the best one is the black one, so that's the population frequency, if you use that. And the purple one is the discrete Laplace, the pink one is the 3-locus discrete Laplace, the orange one is the generous good, and the green one is the Brønder's-Kaplan method. So it seems like, focus on these, that all perform actually pretty well, but also if you had to choose, you would of course use the population frequency. And there are many different measures on these ROC curve, which one is best. So it's really difficult to say that one is better than another unless you sort of are willing to say what's most important for you. One way to look at it is that for a certain false positive rate of 0.1%, you in generally get a higher true positive rate the higher the curve is. Okay. So that's
Just ask what you've got it there. It seems sort of suspicious that they all hit one exactly the same point. So that means all haplotypes above that, everybody gets right.
Yeah.
Is there some obvious reason for that there's a certain class of haplotypes that are a small class that are problematic and the rest are all easy?
I think that's due to all these non-matches. Right.
Oh, they're all the non-match. Oh, yeah.
And up
They
here,
all get it right if there is a non-match.
Yeah. Okay. So there is a simple intuition.
Yeah. But if you think of these as just, decision rules, not being a likelihood ratio, but just some rule that gives you a number, then actually the slope of these ROC curve corresponds to the likelihood ratio induced by this decision rule. So it's interesting to look at how the slopes of these ROC curves is compared to the numbers these estimators give. So this is shown here, and let's just try to look at the population one first. And maybe it's difficult to see, but there's the identity line here. And you see that one is actually, the population one seems to be reporting the likelihood ratio that you are getting from using the method. The same is true for Brønder's in general. It's good, there is some variation around it. And the same for discrete Laplace. So you see there's a tail out here a bit. So it seems like in some of the cases, especially where we have a rare haplotype, it might overestimate the evidential value. For restricting the data to 3 loci, here we always, on the right side, mean that we always understate the evidence. So we give a lower likelihood ratio than the method induces. Okay, so that was the part about trying to compare the different estimators. Now I'm going to talk about population substructure. Martin did a bit about it yesterday. I'll try to do it from the Y chromosome perspective. So imagine that we have a population here that consists of different subpopulations, and the colored squares represent different haplotypes. So as I put in red here, that if a random man, so the donor, and the suspect belong to the same subpopulation, we would expect that they share a haplotype more often than had we had a sample from the population. So meaning that if both of these come from subpopulation 1, they have a higher chance of having a blue haplotype than if we thought they were just random individuals from the population without knowing the population substructure. So that's sort of the idea, and we want to be able to correct for this. And the simplest way probably is to use the theta correction. So that's the idea of it. So the theta correction can be seen as a remedy for not knowing the population substructure. Bruce Weir has made an estimator of trying to estimate theta. I'm not sure if it has been published yet, so I'll just put in it as a personal communication. So the idea is that you have R number of subpopulations, and these are each of size ni, and then you have a certain number of times a certain haplotype has been observed in this particular subpopulation. Then for each subpopulation you calculate the mean within match, and you take the average of all these, and you compute the mean between matches between the ith and the jth subpopulation, and you take the average of that. Then you can estimate theta as the excess within match probability. So if the defense hypothesis is that a random man originating from the same subpopulation as the suspect, you can sort of think of it as two different cases. So either you have a reference database from this particular subpopulation, and then you of course use that without any theta correction. But the theta correction was actually introduced because we think that we have a reference database from the population itself, and we state that these are probably from some of these subpopulations, but we do not know which, and we don't have information about this particular subpopulation. So we want to correct for that fact. And if we use this Baldwin-Nichols model, we can use this match probability. So we have a theta plus 1 minus theta plus the population frequency here. So theta is a population parameter, and this is just the most simple model. There are many possible extensions, but just having this model is difficult to estimate a right theta. So I don't think extensions is that possible yet. Okay, there are a few facts that's nice to note about this match probability, this Baldwin-Nichols match probability. It's larger than theta, and it's larger than the population frequency. So if the population frequency is really small compared to theta, then the match probability is almost just theta. But if it's really large compared to theta, then it's just the population frequency. So it's a sort of a max between these two, or a linear combination between these two. So here we just illustrated in the table. So the first column here is if you have a rare haplotype, and that's if you have a common haplotype. And you see for this first column that the match probability is almost just the theta value. And if you have a common one, the match probability is the haplotype frequency. Sorry. So two examples. So if we have an English reference database, and we state that a random Englishman left the Y chromosome, then we use the population frequency and no theta correction. That's it. So the case is where we have an English reference database, but there's reason to believe that these two individuals come from the same subpopulation. Then it would be better to use a theta correction. But we're sort of in a catch-22 situation, or can we think of it, because what theta correction should we use? We need to estimate a theta that reflects the defense hypothesis. So if they, for example, are from two different large regions, we will need a theta correction that would reflect that. And that's quite difficult, because if we had the reference databases from the subpopulations, it would be better to use those. So it's difficult to estimate or to use the right theta value. And I'm not sure how to do that. But I will move on to an example from Denmark, because we have a Danish family relations database that consists of roughly 9.3 million individuals, both alive and deceased. And we have information about the last residents of these. And if, in this case, because I'm interested in the Y chromosome, I restrict it to men being alive and between 15 to 65 years. And we're down to 1.9 million individuals. We don't have any genetic information of these, we only know where they are. And what's special about this is that we actually know who their father is, or who we think the father is at least. So, okay, so it's not that important. Right now I'm focusing on 11 different regions of Denmark. It's not that important. One thing to note is that Bornholm here is very small. It only has 15,000 individuals, and all the other ones are quite big. So what you can do, because you know who each individual's father is, you can construct pedigrees. So the male lineage pedigrees, without having any information of any genetic information, you can reconstruct these pedigrees. So this is a histogram showing how big the pedigrees are. So there are many that are small, and that's a problem. And the reason is probably because this database only has accurate information on individuals born on 1969 and onwards about relations. So there are some of the pedigrees that should have been connected in the past but aren't, because we don't have information about that. So why do I mention this? So if we give each of these pedigrees a number, a unique number, and assume that all individuals within a pedigree has the same haplotype that is different from all the others, then we can actually try to do theta estimation using this data without having any genetic information. So this NIH now is the number of individuals within the ith subpopulation having a particular pedigree. Okay, and what you see is that over here they are quite similar, the theta within values, but Bornholm sticks out, and that's because it's rather small, so you don't need many matches within that to get a high within match probability. And we can move on to estimate these theta values by using the formulas I showed earlier. So this one is the unweighted estimation that I showed, but it probably would make sense to weight it because now we know the actual subpopulation sizes precisely. So if you weight it by that, you get a smaller theta estimate, which also is corresponds to this part. So that's for the 11 regions in Denmark. You can also look at do a finer grid of another geographical subdivision, having 99 regions instead of municipalities. And there we get a theta value that is 4 times 10 to the power minus 4 instead, and equally you can weigh it again. But I know, so as I said, the pedigrees are probably too small, and I don't assume any mutations. So my impression would be that these are sort of lower bounds for the theta values of Denmark, without being entirely sure, but that would be my impression, and it would be interesting to try to stick these pedigrees together and see how it acts, and also try to impose mutation and see how it goes. But these, I'm thinking of these as lower bounds. That was it.
Thank you, and finished in good time for questions.
Yeah.
Phil,
Thank you, very interesting. But one thing that's always puzzled me about working with the subpopulation type model is, okay, you're allowing for dependence within the population because of the unknown subpopulation, and your theta allows for that. And you're allowing for dependence between two possibly different case-related Y chromosomes. But what I don't think it's allowing for is the dependence between the case data and the database. You're just treating the case data as independently drawn from the database with things you can estimate and just plug in and apply. But in fact, because the case data is also from the same population, it's also correlated with the stuff in the database. And I don't think that's included in the computation.
this goes back to your student's thesis of 20 years ago, I know, but...
Yeah, I agree. But it probably wouldn't be any easier to estimate.
It could make a difference.
Yeah, it could, definitely. I mean, the theta values here is also an average over haplotypes. It might be that some haplotypes are different than others. So it might, could make sense to have a haplotype-dependent theta value. That's also almost next to impossible to estimate.
But yeah, I have some comments on that, but let's hear from Keith first.
Could you go back to the slide where you had, it was the map, that one right there.
Yeah.
What this illustrates to me is that geography makes a big difference. And what bothers me about the United States Y-STR database is that it's actually a convenience sample, which is, it's just basically random. And we know that Y-STR profiles are not randomly distributed throughout the country, but in fact have very constricted geographic issues. So the problem I see is that given that the geography has not been massively sampled, convenience databases, even of 3 or 30,000 in a country of 330 million, can't possibly represent the range of variation, and even using theta values that are averaged, as Bruce did and now you're talking about, may not accurately depict the vast range of values that that Bornholm is a brilliant example. So I'm not really sure that the database is up to the task to which it's being put, at least in the United States.
Yeah, I agree. Yeah. And another problem that I would like to mention the same is that some databases are collected, and if Y chromosomes match, they look for autosomal ones to see if they are related, and somehow, and they disregard, so that was wrongly put, but some databases are collected so that they do not include near relatives. So if they sample independently and have two brothers, they remove that, which is also very wrong because you underestimate that. So there are many problems in collecting proper databases.
Yeah. So my question or comment, I think, follows the same theme. I mean, I'm always troubled by this term defense hypothesis. And the defense hypothesis you put out is certainly not the hypothesis that I would have had if I were the defense lawyer. I would have, if I were the defense lawyer and putting up a defense hypothesis, first it would start with the fact that my client was falsely accused, right? And knowing that there may be some tendency between the haplotype of the true perpetrator and the haplotype of somebody who is falsely accused of doing a crime.
That's to help the defendant. That's for helping the defendant.
What's that?
It helps the defendant. So, go back.
Yeah, but this is close to the point I was going to make, but it helps the defendant in a way that your analysis doesn't take into account. I think that.
Yes.
Sorry.
I believe.
Okay.
Because so people falsely, if I'm falsely accused of a crime, it may be much more likely that the true perpetrator is somebody who's a relative of mine who would share the true haplotype than would be true for a randomly chosen person from the population. And if that's not taken into account, then it seems unfair to the defendant to state as the defense hypothesis something that will lead to an estimation of allele frequencies that understates what the true values have to be.
But so
yeah, go on.
no, so if you assume that they're just from the population as a whole, you use the population frequency, and this by using this Ball-Nichols model, you get something that is like bounded below by this, so you get something that is a higher match probability, meaning a lower likelihood ratio. Okay, so that's one thing. The next thing is that the way I put this defense hypothesis is to match the theta method that has been developed. So that, I mean, if you do something to say something different, it's very, very difficult to get a method to estimate things. But if you pick it like this, you have the theta method developed by Ball and Nichols. And actually, that detail of that, David, you probably have to correct me if I'm wrong, is that the theta correction was developed in the way saying that these two individuals come from the same but unknown subpopulation. So it's an average over what possibilities there are, not that both of them are from Bornholm. If you state that, it's something different than saying that it could be from any subpopulation.
Nora.
I mean, just as a more general commentary on that, as Keith mentioned in his talk, this whole literature has evolved with HP and HD, and I think it's just hugely problematic because it is not up to us, nor do we know what the prosecution, maybe you can guess, but in particular what the defense hypothesis is. And it's not up to us to guess what might help the defendant, among other things. Sometimes the question is about an alternate defendant, or sometimes you're comparing some other exclusionary person, and why don't we just use H1, H2, H3, H4, and then say scientifically what it's doing? It just seems less problematic than putting all this stuff in the middle that's legal and not science.
But I think that's further down the road. I mean, we're having problems with just estimating population frequency, and that's difficult. I mean, the other stuff is complicated. It's even more. It is interesting and it is, useful, but it's also difficult.
Yeah, I mean, just so why confuse that with guessing prosecutor and defense? Just say what you're doing.
That's a simple thing. I mean, you're starting out from a simple origin and try to use that, and then we can complicate it later. That's at least my impression from it.
All right, good. I've got quite a few comments on the discussion so far and the talk, and I've been itching to get them in, and I do have time. So I've been trying to be a good chair and stand back, but
well, that ends.
In the end by this, we've still got several minutes to go. So just one point that is kind of relevant. One of my kind of favorite kind of complaints is I don't think it's helpful to talk about the alternate sources being a random man. I think that there is the alleged contributor, and then there's a list of other men who could be the contributor. And talking about it being random kind of implies uniform, suggests uniform probability distribution, which isn't appropriate, and so on. So, and I think that's kind of relevant for some of these things. And so this sort of ties in with several people's points, because the defense hypothesis might be if and this is the really relevant issue with Y chromosomes, is that it could be a paternal lineage relative, and there's all kinds of issues, so I often make this point that Bill made, is that if you've got the wrong guy, then the right guy might resemble him in many ways, making it more likely that he's from the same area, looks similar, something like that, those kinds of things, and therefore increases the probability of being a paternal lineage in a way that's very hard to assess, but we have to sort of somehow try and take this into account. So theta's trying to get at, in a very crude way, the shared ancestry between the suspected contributor and the alternate contributor. And you can think about that very explicitly with Y chromosomes because of the uniparental lineage. So you go back, the suspected contributor, if you want to focus on him, has got father, grandfather, great-grandfather, all expected to have the same Y chromosome, depending on how many markers you've got.
Yeah.
And then all of their male descendants are expected to have the same Y chromosome, and I think that's what it's trying to get at. So it's going to depend very much on the scale. So what you've done here with dividing Denmark up into regions is obviously a kind of step forward, but if you had a finer scale, you would probably get bigger values of theta, and they might arguably be more relevant in some cases. So
I agree that it's very important, but I also agree that I think that it's more difficult than taking the very simple of taking a random man. I think that's the easiest thing you can do, and if we're struggling with that, it might be sort of difficult to move forward. But I think I agree in casework, it's not necessarily the best hypothesis.
Yeah, okay, but I mean, whatever it is, in any case, there's just, there is a suspected contributor or alleged contributor, and if it's not him, there are other guys who could be the contributor, and that's all you've got. So coming back to Phil's issue about the database, yes, there probably is some dependence, but I think there's a kind of particularly strong dependence between the suspected contributor and the alternate source of the Y chromosome, and so that makes modelling other dependencies relatively unimportant, and we do the modelling pretty crudely because of all these difficulties that I've been highlighting. It's hard to get it right, and so you have to do it in some kind of conservative way, and we can think about that with autosomal. It's a bit easier to think about doing this in a conservative way because you can measure at different scales and with available data and get the range of values and then think about what's a fairly conservative value. But with Y chromosome, it's quite hard because there's a pretty large, there's an interesting number, is how many men expect to share your Y chromosome. Obviously, it depends on how many markers there are.
That's exactly why I try to get the data from Denmark, because we have some pedigree information. We don't have genetic information, but we have some pedigree information, which could be quite valuable.
Yes, but then you have to have a sort of evolutionary model because it could be going back 50 generations, and so you're never going to have a database going back far enough and modeling. But
maybe in Iceland.
But typically for the number of the expected male lineage relatives, conditional on that you exist, that's informative about the number of other men who might have the same Y chromosome, and it would typically be in the thousands, depending on mutation rates and population sizes and all this kind of thing, and all of those guys expect to have the same Y chromosome. And there is some finite chance that the true source of the DNA is one of those guys, and it's very hard to model that probability, and so all of this kind of helps a bit, but I still think it's very problematic that in terms of, exactly because of the point that Bill's making, because you've got the wrong guy, that sort of enhances the probability that the right guy is one of these ones that has the same Y chromosome.
But it could be helpful to try to formulate this defense hypothesis that we're looking at then. Yes. Because I'm having a problem finding the right hypothesis. And this is a simple one that we can do something about.
Your extra high value for theta in Bornholm, was that what it was called? The small place? You see, if you divided up all those other regions more finely, you'd also similarly get a large value, or maybe not as large, because it's an island, I gather, so obviously that affects things. But any other comments?
Is what you were saying then, Dave, about the defense hypothesis, those H1, H2, you should be actually going out and finding all the ancestral descendants and ruling them out effectively?
Well, I don't think that's realistic, because actually eventually, the more markers you get, the further you have to go back in time. But in the sort of numbers of how many markers are we typically talking about in the data you've got? That,
27. I think
yes.
in long
Okay. So
pages.
that's already getting large, but that means probably you have to go back even a few tens of generations, and you've still got a good chance that the ancestor will have the same chromosome because mutation rates of the order of 1 to 500 generations or something like that.
A few lots of that has a much higher
Okay, so
mutation,
that helps, yeah.
Yeah.
But
it is difficult.
but yes, I think you probably won't ever have pedigree information deep enough that. So yes, all you can do is some kind of theoretical calculation about how many guys might match, and that seems to me, that it needs this explicit calculation with number of loci, with mutation rates. Then you have to assume some demographic model, but then you could at least be descriptive about the distribution of the number of men sharing the same Y chromosome, and that seems to be the most useful information that you could give, and then courts can assess, how likely it is that it's one of those guys that could have been the source. Anybody else got any final comments? We've got a minute to go, but if not, then thanks very much, Mikkel.